What's up, YouTube? It's your boy, JOHAJBRAHAM. That was not fast, but I need to make it even faster. I need to be fastest. We back 1 hour organic chemistry. 1 hour organic chemistry. Tai Chi. So last time, if I remember, on the basis of lecture notes, I was at this part. Reaction mechanism. That's where I was. Did I set the timer? No. One hour. 45 minutes. 30 minutes. 15 minutes. 20 minutes. Damn my face. Ah. It hurts. It hurts, god damn it. It hurts. It hurts. Hi, bro. I remember this name. What's up? Organic. Orange. Yo, what's up? That's the last thing I wrote on my notes. n stereocenter to raise to n possible stereoisomers. Okay. Inverted configuration. SN1 mechanisms. So we start from a tertiary carbon. We move to the we move to the transition state, or yeah, transition state. Then we get, what's this one called? Ionic form. The bromine is replaced. Looks like bromine is replaced, and there's two ways you could attack the carbon. That's inverted, that's same configuration. Okay, depends on from which side you attack. And this one is called, oh, there's no name. When there's reverse configuration occurs, it's called Walden's inversion. Okay. Okay. Is there a limit on how much I can add? Following page discussing Walden's inversion in your lecture notes found on page 191. Okay, okay. The next section explains the solvent effect and the nucleophilic substitution reaction. Here's the breakdown of what these pages explaining. How solvents react with ions. The notes first explain solvatization. How solvent molecules surround and stabilize ions. Anions are solvating primarily by protic solvents, anions with the negative charge. Through formation of hydrogen bond, cations are solvated by both protic and aprotic solvents like DMSO or DMF through the donation of electron pair to the positive charge. Solvent effects on SN2. The effect of SN2 reaction is different because nucleophile is involved in the rate determining step. Now let me see what type of questions. How do polar aprotic solvents speed up SN2 reaction? Can you give an example of protic versus aprotic solvents? How do these solvent choices affect SN1 reaction? Okay. Effects of SN2 reaction is different because nucleophile is involved in the rate determining step. Protic solvents slow down SN2. These solvents often slow down SN2 reaction because they strongly solvate the nucleophile, making it less reactive. Okay. Solvent effects on SN1. These solvents slow down SN2 reaction because they're strongly solvate, surround the nucleophile, making it less reactive protic. Solvents like DMSO or DMF are preferred for SN2. They increase reaction rates by a factor of 10 raised to 10 raised to 3 to 10 raised to 6 because they dissolve ionic reagent well and stabilize the transition state without caging the nucleophile as strongly as protic solvents do. Charge distribution. Generally, if the starting material is more charged than the transition state, a less polar solvent speeds up the reaction. If the starting material is less charged than the product's transition state, a polar solvent is better. Matthew legit, yo! What the hell is Hugo doing here? I don't know. I banned or I blocked Huey for 1 day. He was banned for 1 day. And I think he's an improved person because he's not talking too much. 1 day, yeah. Because they dissolve ionic reagents well and stabilize the transition state without caging. In summary, the transition from Waldron's inversion to this page highlights that when the mechanism determines the stereochemistry, the solvent choice determines the speed and feasibility of the reaction. Okay. Alright. I just wanna confirm. Bollock, hell yeah. SN1, SN2. Involves state which is kinda hard to observe, while the SN1 has an intermediate stage where it's easy, where it's observable. Compared to the what you're working on right now. I'm looking into organic chemistry because I got a lot to learn on organic chemistry. And wait. Homolumo, heterolytic cleavage, homolytic cleavage. That's something. That is something that's on organic chemistry. Transition state versus intermediate. Leaving group, heterolytic cleavage. SN1 substrate determines the rate. SN2 both substrate and nucleophile determines the rate. Okay. Both substrate and nucleophile determines the rate. Okay, I'm starting to reaction. So how nucleophile PHILE nucleophile is an charge, and how wait. Protic solvents slow down SN2. These solvents often slow down SN2 because they strongly solvate the nucleophile, making it so protic solvent solvating nucleo means it but if I understand, protic solvents are also negative charged, like So could you explain a bit on how is the protic? That's a great shot. Shut the fuck up. I don't care what you think about me. Transition state versus intermediate. You are right to distinguish between these two. Black box, kinetics, and nucleophile. In SN2 reaction, the rate is indeed determined by both the substrate and the nucleophile. Rate equals, okay, big concentration, okay. They must collide for the reaction to occur. The concentration and strength of the nucleophile directly impact the speed, how perotic solvents solvate the nucleophile. Your confusion about water's negative charge is common one, while oxygen atom in the water is electron rich. Water molecules are neutral overall but polar. Here's how solvation of a negatively charged nucleophile works in a protic solvent like water. The dipole effect. Water has a dipole, meaning it has a partial negative charge on the oxygen atom and a partial positive charge on the hydrogen atoms. Ion dipole interaction, where you dissolve a negatively charged nucleophile in the protic solvent, the positive ends of the solvent molecules orient themselves towards the negative nucleophile. That's what it's here. Okay. I should have just looked here. Ion dipole interactions between the negatively charged species and water. I have a small doubt on nucleophile. Is it always negative, or nucleophile could be positive? No, nucleophile is always negative. So here, this one's a nucleophile, the other one's a electrophile. 20 minutes? Whoa. It's not good. That's not fast. These solvent molecules form a shell around the nucleophile for SN2 reaction to happen. The nucleophile must break out of this solvent shell to attack the substrate, which is why protic solvents often slow down SN2 reaction. Mm-hmm. DSMSO can solvate a cation better than it can solvate an ation. And ation? Did I just say that? If I have to say ation, that means my brain sent a signal to my larynx, this thing, that when you read the word anion, make sure you put that T and produce the sound. My brain did press that button to make that sound. False input, misinput. Misinput. That's not what we want. We don't want misinputs. We never want misinput. Who's we? The rest of the cells in my body, I guess. Yep. So a protic solvent like water can reduce or solvate both electrophile and nucleophile. But if I understand, substitution reaction only involves nucleophile, and even the leaving group is also gonna be negative charged. So I'm wondering, in the case of water, is it better at solvating an electrophile or nucleophile? What's the relevance of that question? No, there's no actual relevance if I think about it. Why is it taking this much time? Effects of SN1 reaction, solvent effect. Depending on the polarity of the starting material, transition state and product, the reaction can either be sped up or slowed down by a more polar or protic solvent compared to the reaction in a non-polar solvent. Depending on the polarity of the starting material, transition state and product, the reaction can either be sped up or slowed down by a more polar or protic solvent compared to a reaction in a non-polar solvent. Vibe of Messi won. Oh, today was Argentina? Argentina versus what's the other team? So that's the MSO. Yo, it's taking an incredible amount of time compared to. What are you studying in inorganic? It's like the normal 12th standard thing. SN1 substitution reaction. Basic inorganic stuff. Egypt. Oh, Egypt. Are they really good players? Whoa, it's taking too much time. What happened to Notebook LM? The fuck happened? Keep Jenna, stop. It has to go through all the 10 PDFs. You know what? Okay. Based on the provided lecture notes, a protic solvent like water is highly effective at solvating both electrophile and nucleophile, but it interacts with them using different parts of the molecular structure. Yeah, I'm asking which is better. SN1 does not form a transition state. You are right. SN2 forms transition state. Wait. SN1 forms intermediate state, which is more observable. So, water solvates anion through ion dipole interaction, specifically forming hydrogen bonds. Yeah. Water has acidic hydrogen with a partial positive charge. It creates a strong solvent shell or cage around a negative nucleophile. Okay. While water is very good at this, it makes the nucleophile less reactive SN2 reaction because nucleophile must break free from the strong solvation shell to attack the substrate. That should be the same case for SN1. So you're studying general organic chemistry, I guess, or maybe haloalkanes, haloarenes. I guess those are there. It's mainly reaction mechanism. We got substitution, elimination, halogenation, bromination, ozonolysis. There's more other things. And at the last part, there's organic, not organic, biochemical reactions involving proteins and shit. And I'm nowhere close to the last part. I need to complete everything. Also, I need to learn the NMR interpretation. Spectroscopy interpretation. Because I feel like that's a really important thing if I work in a lab or something. I need to know how to understand which chemical did I just test, or how's the bonds. Yeah. Water has more acidic hydrogen with partial positive charge. Water solvates cations by donating electron pairs from oxygen atom. Yeah. Which is better at? Better depends on the reaction mechanism you're trying to achieve. SN1 reaction, water is exceptionally good at solvating the electrophilic carbocation. This stabilization is the primary reason protic solvents are used to promote SN1 mechanism. Oh, it stabilized the carbo. How well do you know organic as of now? I would say my knowledge is very low, bare minimum. And the main thing, whenever I study, I need to. It takes for me it takes a bit time to simulate what I just read. Maybe that's just for me. Studied isomerism. Is it where the multiple structures, possibility of multiple structures, like benzene? I forgot the name. What's it called? Benzene can split between 6 separate structures. I forgot the name of that. Yeah, okay. Fuck. What's it called? Is it called isomerism? Isomerism of benzene? No, there's another name. Boat and chair configuration. Yeah. I don't know about that one. I've seen in the lecture. No, not isomers. There's another name. Let me check it out. I wrote it down. Resonating structure. Resonance. Yes, that's the name. Resonance. Good one. Boat and chair configuration. I've seen that in class, but I never understood what it was. I think I need to learn that. So in the case of SN1 reaction, polar solvent stabilize the intermediate or the cation. What about the nucleophile though? In summary, water is structurally equipped to handle both. It uses hydrogen to cage the nucleophile and oxygen lone pairs to stabilize the electrophile. Okay. If the dipole effect of water results in solvating of the solvating of the how is it's just that the pi electrons are in the resonance with the single bonds. That's why you see benzene displayed as a hexagon inside. You also see benzene displayed by a hexagon inside of which is a circular ring. That is because of resonance. Yeah, that's because of resonance. And there's another name for interchanging double bonds. What the fuck? It was called C. It started with C or something. In Not covalent, no. Uh, co Copper? No, no, no. Damn, my memory's fucked up. Conjugation. Damn. Conjugation, yes. How can I be a chemist if I can't remember basic rudimentary terms? I guess I gotta work twice as hard. Conjugation, yes. So, in the case of the dipole effect of water results in solvating the nucleophile. Same goes for same case for maintaining the carbocation, yeah. Carbocation. How is the nucleo gonna attack Yeah, that is the reason for its aromaticity and Huckel rule and all 4n plus pi electrons and sp2 sp3 conjugation. Sp2 sp3. Oh shit. Like when I just read sp2 sp3, my brain is not coming up with what exactly sp2 and sp3 is. Yeah, I could remember it when I refer my notes, but when I read that, my brain is not simulating what exactly is sp2 and sp3. That's a problem that I've been noticing for a long time. Like I've written down what sp2 is. If I look it up, I could now remember it, but I need to train my brain to get what I want when I read it inside my brain. What am I even saying? You understand what I'm saying, right? That is hybridization, brother. For calculating, you just need to add bond pair plus lone pair of that particular atom at which you want to calculate the hybridization of. Yeah. Carbon, hydrogen. Again, when you said hybridization, my brain is not coming up with what exactly hybridization is. I might have written it down somewhere, god damn it. I think it's part of general chemistry. Yes, yes, I do remember that. Single bond sp3, double bond is sp2, uh, and uh, overlap. There's the yeah, sp2, sp3. These are overlapped orbitals. S orbital of hydrogen with the three unpaired orbitals of carbon or something like that. God damn it. I don't have general chemistry. I do have the notes, but I can't find it. But yeah, I need to improve on my memory. It is not there yet. It's not as good as I want it to be. The power of charge attraction. While water molecules surround the ions, they do not create an impenetrable barrier. The sources state that charge attraction is a fundamental force that brings reagents together so they can collide and there you get to know the shape of these orbitals. Yeah, I remember drawing shapes for. I think it's easier to draw orbitals till d orbital. F is fucked up. F is for fucked up. F orbital. I tried drawing F orbital. It's uh it's not hard, but it you need to be precise. The nodal planes, yes. And if I remember, yeah, quantum numbers. I don't know if I looked into. Yeah, quantum numbers. I think that's also part of it. What was it? It's more like probability. Spherical for S, dumbbell for P, and double dumbbell for D. I honestly forgot. D has double dumbbell. It has a donut with two lumps or lobes. I did forget those. Let me search if I got the note. General simplification. What? That's not it. Flower shaped for F? Nah, F is fucked up shape. Introduction to general chemistry. Yeah, electromagnetic radiation, structure of electron shells, quantum mechanical treatment of an atom, radial probability, principal quantum numbers, magnetic quantum numbers, Zeeman effect. Oh, Zeeman effect, yeah, that's where you get to find out the notes. Notice where it's absolutely sure that you won't find not even a trace of the electron. Yeah, F orbital looks more like a flower, kinda. Yo, Argentina scored 3 goals? No way. But yeah. P orbital, dumbbell shaped. D orbital, clover leaf shape. With one, that was the one I was talking about. A donut with two lobes. Looks like this. This one, where is it? This one, a donut with two lobes. Then there's the flower, fucking flower. We got nodes. Egypt scored 2 goals. Okay. I have a friend from Egypt. And yeah, that's cool. 45 minutes? Okay, right now I should focus on the one I'm studying. You're gonna go get some beer and celebrate? Let's go. Underage beer drinking. Let's go. Charge attraction is the fundamental force that brings reagents together so they can collide and react. The positive charge of carbocation and negative charge of electron-rich lone pairs of nucleophile exert a powerful pull on each other that helps them break through their respective solvent shell. Only if my parents don't see this video. I don't think so. Water molecules surround the ion. They do not create an impenetrable barrier. The sources state that charge attraction is the fundamental force that brings reagents together so they can collide and react. The positive charge of the carbocation and the negative charge of or the electron-rich lone pairs of the nucleophile exert a powerful pull on each other that helps them break through their respective solvent shell. The slow step versus fast step. Okay, so you're telling me even though nucleophile undergoes solventization, it still is being attracted by the carbocation or is attracted towards the carbocation. Then what's the point of water being attracted to water being surrounded by the nucleophile? The slow step versus fast step. As in one reaction, the hard part is already over the cation, carbocation is formed. Rate to the limiting step forming the carbocation from starting material is slow and requires high energy. The attack step, once that the higher energy carbocation intermediate exists, it is extremely reactive. The source label the attack of the nucleophile of the carbocation as fast. The source, source here. Attack of the nucleophile on the carbocation as fast because the intermediate is so unstable it reacts with the first available electron-rich species it can find, often becomes a perfect solvation shell, can even fully lock it away. Often before a perfect solvation shell can fully lock it away. Right after it forms the intermediate, it locks it away. Solvolysis. The solvent is the nucleophile. In many of these cases you're studying, like in one of your tables, the reaction is a solvolysis meaning solvent water acts as a nucleophile. Because the carbocation is surrounded by water molecules, the nucleophile does not travel through the solvent to find the electrophile. It is already in direct contact with it. The water molecules use their lone pairs to stabilize the cation and then immediately use those same lone pairs to form a new bond, as seen in the mechanism. Seen in the mechanism for tertiary butyl bromide reacting with water. Dynamic nature of solvation. Solvation is a dynamic process, not a static one. Solvent molecules are constantly vibrating, rotating, and swapping places. Uh, for a reaction to occur, ions must collide with enough energy to displace some of the solvent molecules. The sources note that it is actually easier to break the ion-dipole interaction between a weak base and a solvent than a strong one. Strong base and a solvent, which is why another certain species like iodine becomes stronger nucleophile since protic solvent despite being solvated. Iodine is negative, right? Nucleophile. The sources know that it's actually easier to break the ion-dipole interaction between a weak base and a solvent than a strong one, which is why certain species like iodine becomes stronger and nucleophiles in the protic solvent despite being solvated. In short, carbocation is so reactive and charge attraction is so strong that they overcome the cage effect, especially since the nucleophile is part of the cage itself. Okay, I kinda understand how the polar protic make SN1 faster, but still if we compare SN1 reaction where one has a protic solvent like water and the other has a solvent that only cons no. It's a negative charge. Would that result in even imagine the people who discovered the SN mechanism, what exactly were they doing with their lives? I always like whenever learned something a little bit complex or if something that is really tiny and hard to observe, like what? Where did you start? Where did you start your thought process? I don't know. But hey, they did. I need to get some water. Even faster SN1 reaction? That's what I was gonna ask. Also, another part is I want you to explain how the SN2 reaction gets slowed down by the protic solvent. As I know, the protic it undergoes what? Solvation. And there's no intermediate that the solvent can stabilize. So this time it's just the nucleophile being surrounded by the SN1 reaction why protic solvents are protic solvents are essential. Wait. Oh, come on. SN1 reaction. Why protic solvents are essential? In an SN1 reaction, the rate determining step is the formation of the carbocation intermediate. Stabilization is key. This step involves converting a less polar starting material into a highly polar carbocation and leaving group. A protic solvent like water is critical because it stabilizes the formation of the carbocation through solvatization. We see 1 hour. That's it. 1 hour, that's it. One page. This step involves converting a less polar starting material into a highly polar carbocation and leaving group. A protic solvent like water is critical because it stabilizes the formation of the carbocation through Solventization, which significantly decreases the activation energy. Wait, what? A protic solvent like water is critical because it stabilizes the formation of carbocation through solventization, which significantly decreases the activation energy. It decreases the activation energy to get to the carbocation. Okay. Okay, solvent decreases activation energy because it stabilizes the carbocation. Okay, okay. If you spend energy, no. Okay, I got even more questions now. Like the naked nucleophile scenario. You said just the solvent of just negatively charged nucleophiles might be faster because there's no solvating effect. However, the sources show this is incorrect for SN1. Without a polar solvent to stabilize the developing positive and negative charges of the transition state, the energy barrier to form the carbocation might be massive, making the reaction much slower or even impossible. Just because, okay. I was focusing on making sure the nucleophile is not surrounded, but it results in less stable carbocation, which makes the reaction even slower. Okay. Kinetics. Remember that the reaction rate of SN1 is independent of the nucleophile. Reaction rate of SN1 is independent. Reaction rate of SN1 is independent of the nucleophile. Reaction rate of SN1 is independent of the nucleophile. Even if you had a naked nucleophile ready to attack, the reaction can be reaction can't proceed until carbocation is formed, and the forming that carbocation requires the stabilizing help of a polar/protic solvent. You know what? Why not read the book? The book itself. Clayton's. Let me see how big is the book. Okay. So you're telling me that I better Where's the book? That's unfortunate that I don't have the book. I have the book, but it's not on the PDF form. Where's books? Clayton, where is this? $1,200 pages, okay. Where is this though? These are the table of contents. What is organic? Organic determining organic structures, organic reaction, nucleophilic addition to carbonyl group, nucleophilic substitution to carbonyl group, diastereoselectivity, organic chemistry today. Okay. SN1 needs protic solvents to help overlaying group of the stabilize the resulting cation. How? Okay. SN2 is hindered by the protic solvents because they lock up the nucleophile in the cage of hydrogen bonds. Depending on the polarity of the starting material, transition state, and the product, the reaction can either be sped up or slowed down by a more polar solvent compared to the reaction in a non-polar solvent. SN1 reaction, the formation of polar intermediate is the rate limiting step in SN1. It reduces the activation energy. Effects of SN reaction. Solvent effect. Use of pure H2O can significantly speed up the SN1 reaction. Take care, sometimes the solvent may react as a nucleophile itself. Relative rate 100 to 80% water, 20% ethanol. Okay, YouTube. 1 hour. I'm gonna end this one and start with next timetable. Fuck, tomorrow's timetable. But I also have to look into the project. Send another email. Okay. Peace out, YouTube. 1 hour. Organic chemistry means 1 hour. I don't want to push the agenda.